Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on September 11th, 2025, just yesterday. The standout finding is that tiny gains in single-step accuracy can compound into exponential increases in how long a model can keep executing a task without failure, which reframes long-horizon failures as execution problems rather than reasoning limits. The paper is titled, "The Illusion of Diminishing Returns, Measuring Long-Horizon Execution in LLMs," and the implications for model scaling and test time compute are quite significant. The authors show that thinking-style models avoid self-conditioning traps and execute far longer sequences, while bigger non-thinking models still degrade as errors accumulate. On X, commenters highlight that small per-step gains explode task horizons, and that execution, not reasoning, breaks long runs. One thread claims thinking models sustain hundreds to thousands of steps, with Horizon GPT-5 surpassing 400 plus and doubling Claude Sonnet, drawing solid engagement around 90 likes. The previous figure set the stage for measuring execution, and Figure 1 summarizes the key claims. The top row illustrates how small-step accuracy gains translate into steep growth in task length, and it contrasts expected stable accuracy with the observed drop caused by self-conditioning, which means prior mistakes in context trigger further mistakes. The bottom left panel shows longer horizons as model size increases. The center bottom panel reports that thinking-style inference pushes single-turn horizons far higher. The bottom right panel indicates larger models become more vulnerable when prior errors appear in context. So the previous figure introduced the big claims, and Figure 2 shows the math-driven punchline. The blue curve plots horizon length against step accuracy, and it shoots upward once accuracy passes about 70%, which means tiny per-step gains yield huge increases in how long a task can run. The dashed green line gives a plain exponential for comparison, and the blue curve surpasses it. This gap clarifies why modest accuracy improvements can translate into dramatic practical reliability. Alright, the previous figure highlighted the steep horizon gains from small step accuracy bumps, and Figure 3 explains the experimental setup that isolates execution. The left panel frames long tasks as repeating retrieve, then compose steps that update a state, while the plan is user-provided. The right panel instantiates this with a key-value dictionary and a running sum, which removes planning and world knowledge so execution errors become visible. Okay, the previous figure outlined the task design, and Figure 4 reports what happens as turns grow. Panel A shows task accuracy collapsing with length, yet larger models fall more slowly, so they survive many more turns. Panel B separates per-turn accuracy, which starts near perfect for most models, but steadily degrades with longer histories. Panel C then converts this into horizon length, rising sharply with model size, without obvious diminishing returns. Well, the previous figure documented that thinking reduced self-conditioning, and Figure 7 benchmarks how far models execute within a single turn. The left panel shows non-thinking models topping out at only a handful of steps, even for large systems. The right panel reports that sequential test time compute with reasoning tokens boosts horizons dramatically, with reinforcement learning trained variants pushing much farther. The spread is striking because one model exceeds 1,000 steps, while the next best lands near 400. Wrapping up, two takeaways stand out. Small boosts in per-step accuracy translate into exponential gains in how long tasks run, and long-horizon failures mostly come from execution drift and self-conditioning, not missing knowledge. The broader implication is clear. Scale plus sequential test time compute unlocks durable agents. That is it for the AI Research Roundup. I am Alex. Thanks for listening.